Hi there. We spoke in the previous video and in the lectures about the atomic orbitals of carbon, and I said that carbon has 6 electrons, and what we do is we fill up we put 2 electrons into the 1s orbital, so that's filled up and that's low energy, so we don't worry about that. And then we come along to our second shell of electrons, and we put 2 electrons into our s shell, and we put 1 electron into 2 of the p orbitals. I've put it into the px and py, but these are all the same energy, so it doesn't matter which electrons these are. And I said we filled up these electrons like this. I also told you that when we come to make molecules, what we're going to do is we're going to join atoms together in order that the atoms can get 8 electrons. And you do that by sharing electrons with one another. Now, I hinted in the last video that these atomic orbitals can help us begin to understand the structure of molecules. Now, unfortunately, that's only part true. Okay, these atomic orbitals don't tell the whole story. Okay, and for the whole story, let's consider methane. Okay, here's methane. Methane is carbon, that's shown in grey, attached to 4 hydrogens, so like this. Okay. Now you'll see that this is the hydrogens are attached as what's called a tetrahedron around this carbon atom. All the bonds are the same length. Okay. And all the hydrogens are arranged equally. Okay. Now, if we go back and have a look at our atomic orbitals, we can see that there's a bit of a problem here. Our p orbitals are, for instance, perpendicular to one another, so that's 90 degrees to one another. And our s orbital is, if you remember, the s orbital is lower in energy. So if you were to think about what you'd expect based on only the atomic orbitals, you would probably come up with the answer that you'd expect 3 of the hydrogens to be at 90 degrees to one another. Those would be the ones that were bonded to the p orbitals. And then 1 of the hydrogens would be attached to an s orbital somehow, and that bond would be a lot shorter because the s orbital's energy is a lot lower. Okay. So that's not what we see though. Instead we get this tetrahedron where everything is equal. And so our atomic orbitals are kind of letting us down a little bit. And we don't know, so how do we reconcile the fact that we have these atomic orbitals, and then the atomic orbitals only don't really explain the bonding of methane, which is probably the simplest organic molecule. Okay. And the answer to that question was proposed by a physicist called Linus Pauling, and he suggested a concept that we now know as hybridization. Okay. And hybridization is simply the idea that, well, these orbitals are merely just the solutions to the Schrödinger wave equation. Okay, and therefore we could just combine these equations and see what we get. Okay. Now, all along I have been showing the orbital pictures, and they look like this, where we have a grey bit and a white bit, or the s orbital is this grey bit. And I've deliberately not explained that. Okay. Because we're talking about an equation, we can talk about what's called phase. Okay. Here is a sine wave. Okay. and you'll see that we have part of the assign function is above the line, okay, and I've shaded that in grey, and part of it is below the line, so it's shaded that in white. So we have a positive phase and we have a negative phase. Okay, the Schrodinger wave equation, it's much more complicated than a simple sine wave, but it too has phase attached to it. Okay, so we have an S orbital. You can think of that as being all positive, for instance, and a P orbital we can think of as having a positive phase and a negative phase lobe. Okay, and what Linus Pauling said was, well, these are just equations, so we can combine these equations and see what happens. Okay, let's do the simplest one. And the first one is where we combine an S orbital with a P orbital. Okay. Now the S orbital, I'm just doing this graphically. I'm not getting into the maths of this. I just want you to get a feel for the general idea that we're mixing these orbitals. Okay. So we have this positive phase and this positive phase and negative phase. And if we add these two together, okay, so we add the S and the P orbital together, we make what's called an sp orbital. The nomenclature just means S and how many P's that we're mixing. Okay, so we make two sp orbitals, and you'll see that negative phase of the P orbital has cancelled out part of the S orbital positive phase, and we're left with this small negative phase here and a large positive phase. Now, okay, and we have two orbitals to begin with, so we end up with two orbitals at the end. Okay, so we have these two sp orbitals. Okay, now these orbitals, whereas the s and the p orbital were of different energies, these two orbitals have the same energy. Okay, they're degenerate, if you remember that word from the previous lecture. Okay, so as they're degenerate, they want to get as far away from one another as possible. Okay, and they do that by arranging themselves linearly. Yeah, so they point as far apart as possible, and that is with 180 degrees between each of these sp orbital lobes. Okay. So sp orbitals arrange themselves linearly with 180 degrees between them in order to get as far away from each other as possible. Okay. Let's have a look at the next one. Okay, so we can do the same with the s orbital and two p orbitals, and this time we get three, because we're combining three orbitals to begin with, three sp2 hybrid orbitals. Okay, each of these has an electron in it because we've started with an electron here, and we have three of these. Again, we end up having this little negative lobe but large positive lobe. Okay, we can do it with the s orbital and three p orbitals. Okay, we have four orbitals that we're mixing, therefore we get four sp3 hybrid orbitals. So we're just mixing these together. Okay. Now, as again, like we saw with the sp orbitals, which were degenerate, these hybrid orbitals, the three sp2 hybrid orbitals and the four sp3 hybrid orbitals, are degenerate in energy, and they want to get as far away from each other as possible. Okay. Now, if you think about how you'd get three groups far away from each other as possible, for sp2, that is trigonoplanar with 120 degrees between each lobe. So there's 120 degrees here, 120 degrees here, 120 degrees here. Okay, this is flat. Okay, perfectly flat. It's a triangle with a lobe at each point on this triangle. Okay, that's what's called trigonoplanar. Okay, planar triangle. Okay, our 4 sp3 hybrid orbitals, they're degenerate. They want to get as far away from each other as possible pardon me, and they do that by repelling one another and adopting this tetrahedral arrangement with 109 degrees between each lobe of the orbital. Okay, they make a tetrahedron. Now, we go back and we have a look at our methane again. Okay, that's a tetrahedron. The angles between each of these lobes is 109 degrees. And it's a tetrahedron because the carbon in this is sp3 hybridized. So we have an sp3 hybridized carbon, and all of the sp3 hybrid orbitals, all 4 sp3 hybrid orbitals, have the same energy. Therefore, the carbon-hydrogen bond lengths for each of these are all exactly the same. Okay. So, by hybridizing our orbitals, we can work out what the structure of organic molecules are, and we can explain the structure of organic molecules. Okay, so we've mixed these orbitals, and in the sp3 we've mixed the s and 3 p orbitals. That gives us 4 hybrid orbitals, and they arrange themselves tetrahedrally. Okay, sp2 mix s and 2 p orbitals. That gives us 3 hybrid orbitals, and they arrange themselves trigonal planar. And then sp we mix an s and 1 p orbital. That gives us 2 hybrid orbitals, 2 sp hybrid orbitals. They arrange themselves linearly with 180 degrees between them. Now, if you're keeping up, you might have noticed that, well, if we've got mixing, in this case, an s with 2 p orbitals, then we've got 1 p orbital left over. Likewise, in the sp case, we're mixing only one of the p orbitals. That means we've got 2 p orbitals left over. Okay, and these p orbitals lie along the original axis that they were going to sit along. Okay, so in this case, in the sp2 hybrid orbitals, what we find is the p orbital is perpendicular to the hybrid orbitals. So if you imagine the sp2 planar system is flat, then the p orbitals come up perpendicular to that and lie through the center of these. Okay. Likewise in the sp, that's linear, and then we have these p orbitals that essentially cross the sp orbitals. Okay. So the p orbitals are in there, and we can't forget about them because they'll become very important later on. Now, to recap, the atomic orbitals of carbon don't directly explain the shapes of organic molecules. Okay. What we do, though, is we can mix these atomic orbitals, we can hybridize them, and that gives us these hybrid orbitals, so sp, sp2, and sp3, and these hybrid orbitals tell us the geometry of organic molecules. In hybridizing, we are left, in the case of the sp2, with 1 p orbital left over, which is perpendicular to the plane of the sp2 hybrid orbitals. Likewise, we have in the sp, we have 2 p orbitals that are perpendicular to one another, and they basically cross this. Okay. Hybridization is an important concept in organic chemistry. It explains much of the structure of molecules, and it's one that we'll have to come back to repeatedly in future lectures.